Hello and welcome to the third presentation in the slider crank mechanism series. In the first two presentations we determined various relative velocities and relative accelerations using graphical methods, but in this presentation we're going to revisit the same example and questions but calculate our velocities and accelerations using analytical methods. These analytical methods include Pythagoras' theorem, basic trig, the sine rule and the cosine rule. If you need a recap on any of these methods, there are separate presentations available. It's strongly encouraged that you've reviewed the previous presentations related to graphical solutions of slider crank mechanisms, and particularly example 1, which in this presentation we will now solve using various analytical methods. Questions 1, 2 and 3 from previous presentations are also included here for you to attempt to solve using analytical methods. And here's an overview of the presentation. The presentation commences with a very brief recap of Pythagoras' theorem, shown here. Brief recap of basic trigonometry, our SOHCAHTOA mnemonic, used to define the sine, cos and tan functions. Don't forget, Pythagoras' theorem and basic trig solve right-angled triangle problems only. Then there's a recap of the sine rule, shown here, and also a recap of the cosine rule, shown here. And the sine and the cosine rule solve non-right-angle triangle problems. Then we commence with example 1, which was solved in our previous presentation using graphical methods. We're now going to solve it using the appropriate analytical methods. So we start with the outline of the problem, then using the velocity vector diagram constructed in the previous presentation, we solve for the various relative velocities using analytical techniques. And then using the acceleration diagram from the previous presentation, we again solve for accelerations using analytical techniques. The presentation ends with questions solved previously using the graphical method. You're now encouraged to solve using appropriate analytical techniques. So for reference, this slide states the approximate start times in minutes of each of the various sections in the presentation to allow you to skip to certain sections should you want to. The next few slides just outline the various techniques that will be employed within the various solutions. Firstly, Pythagoras' theorem, essentially using the generic equation c squared equals to a squared plus b squared, which relates to the diagram here. And of course it's important to remember that Pythagoras' theorem only relates to right-angled triangles here. The next technique relates to basic trigonometry. Again, note that relates to right-angled triangles only. The mnemonic SOHCAHTOA is often used to remember the various trig functions. The SOH here signifies the sine of an angle is the opposite side of the triangle divided by the hypotenuse. The CA here denotes the cos of the angle is the adjacent side of the triangle divided by the hypotenuse. And the TOA relates to the tangent of the angle, which is the opposite side divided by the adjacent side. Here's the sine rule. This applies to non-right angled triangles and is used when one side and any two angles are stated or known, or when two sides and the angle opposite one of the sides is stated or known. Here's the general format of the sine rule. A divided by the sine of A is equal to B divided by the sine of B is equal to C divided by the sine of C. I've just shown the equation inverted here for reference. Note that in the formula, uppercase letters denote the angles and lowercase letters denote the side that's opposite the angle. And finally, the cosine rule, a more complicated rule here, that's where two sides and the angle between the two sides are stated or known, or where all three sides of the triangle are stated but no internal angles. Here's a generic equation related to the subject a squared, this side squared, that's equal to b squared plus c squared minus 2bc multiplied by cos of angle A. And that can be rearranged into this format if we're trying to find the angle. So those are the basic techniques we'll be using to solve for the relative velocities and accelerations within the slider crank mechanisms considered within this presentation. So here's example 1 that was considered in the previous presentation where we solved for the velocities and accelerations using graphical methods. As I said, it's assuming you've seen the previous presentation and so are familiar with this particular problem. But the full question is outlined here. Don't forget with the exercise we're trying to find the velocities and accelerations at the instant of the mechanism as shown here, where our crank is at 60 degrees to the horizontal. This is our connecting rod here to the slider or piston. Example 1 continued. Here's the velocity vector diagram that we determined in the previous presentation using graphical methods. With the graphical method, once we've drawn the diagram to an appropriate scale, we simply then measure the various vectors. What we're going to do in this presentation now is to analytically calculate the various velocity vectors. And then we will compare the accuracy between the graphical method and the analytical method. So example 1 continued. Here we're going to determine angle theta using basic trig. So I'm going to generate two equations from the geometry of our linkage mechanism in this position shown here, and I'm going to solve these equations simultaneously. So the first equation, sine 60 degrees is equal to height h, shown here, divided by 0.2, length of the crank here. So the right angled triangle I'm considering is this triangle, where here's the right angle. And rearranging the equation for h, we simply multiply both sides by 0.2, so height h is 0.2 multiplied by the sine of 60 degrees, called that equation 1 here. And a second equation from the geometry is sine of angle theta is equal to height h divided by 0.8, that's the length of the connecting rod here. This now refers to this right angle triangle shown here. Here again is the right angle. So again rearranging for h is equal to 0.8 multiplied by the sine of angle theta. Call that equation 2. To solve simultaneously, we're simply going to equate equations 1 and equation 2. That removes h from the equation, and we can rearrange directly for sine theta. And that's what's been done here. To find the actual angle of theta, we take the inverse sine function or the arc sine function of our ratio, and that evaluates to 12.5 degrees. So angle theta here is 12.5 degrees. Example 1, solution continued. Here's an alternative method to find angle theta. We're using now the sine rule. So from the sine rule, I can write sine of angle theta divided by the side length opposite the angle, 0.2 meters in this case, is equal to the sine of 120 degrees, shown here, divided by the side length opposite that angle, which is 0.8. Rearranging for sine theta, in other words multiplying both sides by 0.2, we can again determine the angle theta, which of course is 12.5 degrees. So whichever method we use, the basic trig, generating two simultaneous equations solving, or we use the sine rule here, we get the same answer for angle theta. So example 1 continued. So let's now consider our velocity vector diagram from our graphical method in the previous presentation, and let's try and determine the various angles ABC and also lengths AB. Now from our previous presentation we know that the angle to the vertical of vector A to B was 60 degrees. Don't forget vector VBA is this vector here, which is at right angles to the crank AB. So if the angle to the vertical is 60 degrees from our previous presentation, then this angle here at A is 30 degrees, so angle capital A 30 degrees. The angle here is 12.5 degrees. 12.5 degrees shown here. Remember that line CB is normal to link BC. So therefore this angle here, angle C, is 90 degrees plus the 12.5 degrees. So 102.5 degrees is this angle here. To find angle B is simply 180 degrees minus angle A minus angle C. So that evaluates to 47.5 degrees. That's the angle at B here. And from our previous presentation, we evaluated the length AB, the velocity vector AB. It was 2.513 meters per second. Noted as VBA on our diagram. Example 1 continued. So we're going to use a sine rule to try and find length BC, this length here. So BC divided by the sine of angle A is here. That's equal to length AB, shown here, divided by the sine of angle C is the 102.5 degrees shown here. We're arranging for BC, in other words multiplying both sides by the sine of A, inserting the various values, we can determine the lengths of vector BC, and it's 1.287 meters per second, that's VBC. Example 1 continued. We're still considering the velocity vector diagram here. And this time we're going to try and calculate length AC, shown here. Again using the sine rule, length AC divided by the sine of angle B is up here, which is 47.5 degrees, is equal to length AB shown here, divided by the sine of angle C is shown here. Rearranging for AC, simply multiplying both sides by the sine of B, and inserting our values, vector AC is 1.897 meters per second, that's VAC. Example 1 continued. Now we're going to find velocity AD. This is velocity AD. And here I'm going to use the cosine rule. Here's the vector CD. And from the question we know point D is halfway along BC, so 0.5 of BC, that's 0.5 of 1.287. 1.287 is the length of BC, calculated here. So vector length CD is 0.6435 meters per second. Now I'm going to use the cosine rule to find length AD, because I have an angle and I have the adjacent sides to the angle. I have VCA and VCD. So from the cosine rule, AD squared is equal to AC squared, this is vector AC, plus CD squared minus 2 multiplied by AC multiplied by CD multiplied by the cos of angle C here. Inserting the values, vector AD evaluates to 2.13 meters per second, denoted as VDA here. Example 1 continued. So if we compare our velocities between the graphical method shown in the previous presentation and the analytical method in this presentation, we can determine the following percentage difference. For VBA, there's no percentage difference because vector VBA was calculated from information given in the question in both solutions. Vector VCA, we find a difference of 2.5% between the graphical method and the analytical method. The graphical method is 2.5% smaller than the analytical method. And for VDA, there's a 1.4% difference. The graphical method is 1.4% smaller than the analytical method in this case. So overall, quite reasonable values from the graphical method when compared to the actual values in the analytical method. So example 1 continued. Let's now consider the acceleration diagram from our graphical method. And we're now going to try and determine these various values that were scaled on the graphical method. We're going to try and calculate these values using the analytical method. Example 1 continued. So here's the commencement of the analytical solution. I've added the acceleration vector diagram from the previous presentation here for reference. First of all, let's define some angles. Angle capital A, that's actually the angle in here, is 60 degrees. Angle B, that's actually this angle here. So that's the 30 degrees angle here added to the 12.5 degree angle here. So that summates to 42.5 degrees. So that's angle B determined. And angle C is calculated from 180 degrees minus angle A minus angle B. So using the above values, angle C evaluates to 77.5 degrees. That's this angle here. So knowing these three angles are A, B and C here will allow us to consider this non-right angled triangle highlighted in red, from which we can begin to calculate some of the unknown accelerations. And notice from the diagram, length AB is 31.58 meters per second squared. That's this acceleration here. That was calculated in the previous presentation, knowing the angular velocity of the crank and knowing the length of the crank. Example 1 continued. I just repeated the various angles here and the lengths AB for reference. So we're going to use the sine rule now to calculate length BC of our triangle. That's this length here. So the sine rule formula is length BC divided by the sine of angle A is equal to length AB, that's this length here, divided by the sine of angle C. Rearranging for length BC, in other words multiplying both sides by the sine of angle A, and inserting the values, we calculate length BC as 28 meters per second squared. So that's the linear acceleration of the conrod BC. Example 1 continued, just repeated the various information for reference here. Now we're going to use the sine rule to calculate length AC. That's the length of this line or this vector shown here. So for our application of the sine rule, the formula generated is AC divided by the sine of angle B, angle B is in here, is equal to AB divided by the sine of angle C. Rearranging for AC, in other words multiplying both sides by the sine of angle B, and inserting our values, we evaluate length AC as 21.85 meters per second squared. So that's the acceleration of point C, the piston or the slider, relative to fixed point A, centre of rotation of the crank. Example 1, solution continued. Just repeated some information here for reference. Angle C we calculated was 77.5 degrees, that's the angle in here. And also we calculated the lengths of vector CA from the previous slide. So now we're going to calculate the acceleration of point D, that's halfway along the conrod, relative to point A, centre of rotation of the crank. And we'll use the cosine rule to solve for this. Now we know from the calculations undertaken so far the acceleration vector BC is 28 meters per second squared, and we know that proportionally DC is half of BC, so we can calculate the length of vector CD, shown here, to be a half of BC. So that's a half of 28. So that's 14 meters per second squared. So that's this acceleration shown here, related to length DC of my triangle. We're using the cosine rule here because I have an angle and the two adjacent sides to the angle, so that will allow me to find length AD, this length here on our triangle. So from the cosine rule, AD squared is equal to AC squared plus CD squared minus 2 multiplied by AC multiplied by CD multiplied by the cos of angle C. Inserting the values, AD squared evaluates to 541, and square rooting both sides, the length of AD is 23.26 meters per second squared. We calculated 22.25 meters per second squared from our graphical method. Example 1 continued, and now we're going to calculate the tangential acceleration of the conrod BC using Pythagoras' theorem. The tangential acceleration is shown here. It's at right angles to the conrod BC. And on the right angle triangle here, highlighted in red, this is the tangential acceleration vector, labelled as vector C to C dash on the acceleration diagram. So to calculate the length of vector CC dash, we're using Pythagoras' theorem, and that's going to be the hypotenuse of this right angled triangle labelled BC here, which is 28 meters per second squared from our previous calculation. Vector BC dash, the vector BC dash, which is a central P to acceleration in this case, and that was calculated as 1.95 meters per second squared. So this is BC dash, 1.95 meters per second squared. So applying Pythagoras' theorem in this case, that's 28 squared minus 1.95 squared, all square rooted. We calculate the tangential acceleration to be 27.9 meters per second squared. So that's a tangential acceleration of B relative to C. Example 1, solution continued. So finally we can now compare the various tangential accelerations between the graphical method used in the previous presentation and the analytical method used in this presentation. If we consider the percentage difference between the two methods for the various acceleration vectors stated in the table, we can see that overall there is a strong correlation between the graphical method and the analytical method. Just if there is a note relating to example 1, here's an alternative analytical solution that could be used, which involves basic trig and Pythagoras' theorem. So to use these alternative methods, notice I've added some nomenclature on the acceleration vector diagram here of x1, x2 and also y here. And essentially we will now consider two right angled triangles. This one shown here in blue and this one shown here in purple. So for the blue triangle, know an angle 60 degrees here and the hypotenuse of the triangle, we can calculate sides x1 and y using basic trig and Pythagoras' theorem. And from the purple triangle, know an angle here and dimension y, we can again use basic trig to find x2 and Pythagoras' theorem to find the length of vector BC. I won't show the associated calculations here, but you could apply the techniques and compare the answers to those found previously using the sine and cosine rules. Now I'll leave you with some tutorial questions related to slider crank mechanisms. These were all analysed in the previous presentation using graphical methods. I would now encourage you to determine the various velocities and accelerations from the vector diagrams using analytical methods. So here's question 1. Here are the answers related to the question. Question 1 continued. Here's a diagram of the actual mechanism. As with example 1, you need to calculate the angle theta shown here using an appropriate analytical method. Question 1 continued. Here's the velocity vector diagram extracted from the previous presentation. We initially were able to calculate velocity vector of A relative to O. And from the geometry we were able to draw the vector diagram and so determine the other relative velocities. Now we have to revisit the question and solve for the relative velocities using analytical methods. Question 1 continued, and here's the acceleration vector diagram, again extracted from the previous presentation. We now have to determine the scaled values shown here using analytical methods. Here's question 2. A slider crank mechanism, but the orientation of the mechanism is different in this case. Again, the answers are shown in the bracket for the appropriate problems. Question 2 continued. Here's a diagram of the mechanism itself. Remember initially to calculate this angle theta from the given geometry. Here's the velocity vector diagram, again constructed in the previous presentation. Notice for reference, in this particular case, point C is not midway along the connecting rod. It's actually 0.4 of the length of the connecting rod from point A. So point C is shown here on the velocity vector diagram. Question 2 continued. Here's the acceleration diagram from the previous presentation, and we now have to calculate these scaled values using the appropriate analytical methods. And finally question 3. A slider crank mechanism here, but the crank OA here has an angular acceleration as well as an angular velocity. In the previous questions, the crank was always rotating at constant angular velocity. In this particular case, we're actually given an angular acceleration here. Again, the answers are shown in the bracket here. Here's question 3 continued. Here's the velocity vector diagram from the previous presentation related to graphical solutions. Notice the various relative velocities have been stated on the diagram for reference. Here's the acceleration vector diagram, again from the previous presentation related to graphical methods. Various accelerations are stated on the vector diagram, again for reference. And question 3 continued. Here's the full completed table from the previous presentation showing the various velocities that were measured from the vector diagram and the accelerations measured from the vector diagram. And again, you have to now calculate these values using appropriate analytical methods. I would encourage you to stop the presentation and attempt question 3. And here's the bibliography used to help generate the presentation. I hope it has been of interest to you, and thank you for viewing.